Welcome to the session on particle swarm optimization. It is another EC technique. So, in this particular session, we can go through the introduction. Since this PSO is developed using different features of natural evolution, so it has a different component such as velocity update, position update, as well as it includes the local best of the each particle and the global best of the swarm. So, we will go through the introduction of particle swarm optimization. Thereafter, we will understand this algorithm through an example. So, working principle of PSO will be understood through Rosenbrook problem, and in this problem we start with initial population followed by the features that are distinct from the other EC techniques. We will discuss them and we will run for one generation. So, we will perform all the hand calculations for this algorithm. At the end, we will show you the graphical example of the same Rosenbrook problem. And finally, we will conclude this session. So, let us begin with the introduction of particle swarm optimization. So, as PSO, so particle swarm optimization, as can be seen, it is referred as PSO. It is motivated from foraging and social behavior of swarm. So, as we know that EC techniques are motivated or mimics the natural phenomena or the process. So, in PSO we mimic the process or the phenomena such as flocking of the bird or school of the fish. First, PSO is proposed by Ebert and Kennedy in 1995. In this particular paper, they proposed PSO as an optimizer for continuous nonlinear function. And as we know, these methods are direct search method which does not need any gradient information. So, even if a function is discontinuous, we can use PSO and other EC techniques. In this paper, the authors have mentioned that PSO is developed using two methodologies. First is called artificial life, another is called evolutionary computation. So, when we say artificial life, meaning that we are mimicking some natural phenomena. So, in this case we have school of fish, flocking of the birds, etc. Similarly, when they move in a swarm or in a group, so they follow some theory which we call it as a swarm theory. So, by using those concepts, PSO is developed, as well as since evolutionary computation idea is used in which the solutions are evaluated and they are compared and new solutions are generated in a process to find an optimal solution for the given problem. So, as we can see here that since PSO is developed using artificial life. So, in this artificial life, swarm searches for the food in a cooperative way. So, since in a swarm there are lot of birds or fishes are there, so they work as in a cooperative manner. So, we might have observed that there is when lot of birds are flying in a sky and they are moving in a one direction. As soon as any bird sees food, then rest of the bird also follow this particular bird when searching for the food. So, the same concept is borrowed and particle swarm optimization is developed. Now, while doing this process, each member in PSO learns from its experience and also from other members for changing the search space pattern to locate the food. Now it is important, why? Because when we talk about this swarming theory, so what is happening is that when one particle is moving from the current position to the another position, so let us assume that it has started from some position and after say 10 generation it reached to the another position. So in between those 10 generation, each particle will know what was its best position. So they keep a track of this position, as well as since their task is to search for the food, or in the parlance of optimization, if we say that we are looking for an optimum solution. So these particles also see which particle has the best position so far. So that is we refer as a global best. So they work individually, look for their best position, as well as they also see the pattern of other members, so that we can find an optimal solution for the given problem. Now, as it is mentioned in the original paper, PSO is developed using the simple concepts and the primitive operators. Now, when we will be discussing the features or distinct features of PSO, we can see that these are different, the concepts of, for example, adding the two vector or subtracting the two vectors. Those simple concepts are being borrowed, and when we will be implementing as an operator, say for variation, those implementation are simple because it involves vector operations. Moreover, PSO is found to be computationally inexpensive, both in terms of memory and speed, and also can be easily implemented using computer programming. So that is the main advantage of PSO. Since the operations are so primitive, the concepts are simple, so we can make the programming or the code for a PSO in a very easy manner. Second is, since it does not involve any kind of probability distribution, so the calculations are simple. So we can say that a PSO is computationally inexpensive in terms of memory, because we do not store any previous solution, as well as we they are also in terms of speed, they are computationally inexpensive. So let us start with particle swarm optimization, how it works. So as we can see here, PSO starts with initializing this population randomly. So we can say that this is very similar to GA, and that is the concept of evolutionary computation, that we start with a set of solutions. But unlike GA, the solutions are assigned with the randomized velocity to explore the search space. So instead of having those operators which we understood as crossover and mutation that are based on the probability distribution, such kind of crossover and mutations are not needed, because the velocity is included into the search, and this velocity with the current position of each solution, the solution is perturbed or the position of the solution is changed. An important point with the PSO is that the solution in PSO is referred to as particle. Now earlier with genetic algorithm, we refer the solutions, the many points. So sometimes we say points, sometimes we say solutions or individuals. But in PSO, just to make it different from the other algorithm, so the point or the solution is referred as particle. So the three distinct features as we talked about earlier, that first is each particle is looking for its best position. So best fitness of the each particle is kept. Similarly, the best fitness of the swarm is also we look for it, and accordingly we update the velocity and the position of each particle here. So when we talk about best fitness of each particle, so basically we target the P best, and the subscript I says that it's a P best of solution I. So this P best is called as the best solution achieved so far by the particle I. How we can know that? When we will be comparing the fitness value of this particle with its previous position. So we keep the column vector of decision variable corresponding to a position which will give me the best fitness. Similarly, when we talk about the G best, so G best is the best solution achieved so far by any particle in the swarm. So earlier it says that its best position, but in the G best it says that the best solution of any particle in the swarm. So we are looking this particular swarm in a totality. And again, if we have to find the G best, we have to look the fitness of the solution. And finally, these velocity and the position update for exploring and exploiting the search space. This velocity and position update will help us to locate the optimal solution. Now, since we know there are 3 different features with PSO, let us go them one by one. We will start with the position update first, because it will behave like a variation operator that will help to change the current position of a particle to its new position. So here the position of a particle I is adjusted as you can see in equation number 1. So this is a particle I in t plus 1 generation. So we are looking for the new position. It depends on the current position and the velocity. So this is the updated velocity V I t plus 1. Now the question comes, how we can find this updated velocity? Let us look at the equation number 2. So the velocity of the particle is updated as, so in this velocity equation we have 3 components. So this is going to be 1, this is another 2 component, and this is the 3rd component. So you can see that since each particle is represented as a since each particle has the decision variable as a vector, so we will realize that these 3 components are the addition of 3 vectors. However, in between, so the component number 2 and component number 3 has some kind of a difference between the 2 vectors. We will discuss the velocity component in the next slide. In this equation number 2, there are various parameters we have used it. So since we are saying I, so I stands for ith particle, T stands for the tth generation counter. So we can say it is a current generation counter. So generally Vi0, so as you can see 0 stands for the initial velocity which we set randomly. Now here this omega, now look at the first term, you can see the omega term here. This omega adds to the inertia of the particle. So it's a weight we multiplied with the velocity, that is the previous velocity. Then there are 2 terms as you can see in equation number 1 and equation number 2, there are C1 and C2. So these 2 C1 and C2 are called as acceleration coefficients. Along with this we have R1 and R2 into the 2 components of in the velocity in equation number 2. These R1 and R2 are called as random numbers which will be lying between 0 and 1. Now come to this representation. So this representation is called Pi. So in the subscript it is written as ILB. So we know the I stands for the ith particle, LB stands for the local best, and T is the current generation. So PILBT is the local best of ith particle. Similarly, if we look at the third component in equation number 2, so this is PGB. So, at the bottom of the slide we can see that this is called the global best, and we know this global best is calculated with respect to the SWAM. Now, apart from that, as we know these two components XIT in equation number 2, this is the current position of the particle. So, let us understand the velocity component in the PSO. So, since it involves, as you can see in the slide, since it involves 3 components, let us understand all of them one by one. So, first component we call it as momentum part. It is because it involves velocity, as you can see. So, the velocity is there. So, we have the velocity of a particle in iteration number t. So, that is why we have this omega times of v. So, since omega is the weight to the velocity, it is called as the inertia component, because we are considering the velocity of the previous iteration t. Now, while we are including this omega vit, it says that it has the memory of previous flight direction. So, as we know that suppose we have a vector say vi, in this case if I am going to multiply say omega vi, so both of them have the same direction. Omega will tell whether the vector is to be shortened or it has to be elongated. Now, the purpose of the first part is to prevent particle from drastically changing its direction. So, since as it is made in a way that if we are moving in one particular direction or with a velocity, then we should not change drastically. Yes, gradually we will change because the other components are added into the velocity. Now, come to the second component. So, this second component is referred as the cognitive part. It is because we always have this component which is called the local best of each particle. What it says that it quantifies performance relative to the past performance. As we have understood, the local best is the position of the particle, is the best position of the particles found so far. So, in this case we are preserving the best local best position of the each particle. So, that is why in the second point we have mentioned it is the memory of the best particle. Now, as you look into the difference part, in this case you can see that what we are doing is we are subtracting the two vectors. So, in a way we are saying that how far this current position from the local best of the particle I, and this particular component is also referred as nostalgia, because we already know what is the local best of the particle. Now, coming to the third part. Now, the third part include the global best. So, here this particular part is called social part. So, we remember that when we are using PSO and it is following the SWAM theory. So, in this case the particle saves its the best position so far, and it also changes the pattern based on the best fitness of any particle in the SWAM. So, that is why it is called social part here. This particular part quantifies the performance relative to the neighbors. Now, if you look at the difference here on the top, this says that what if since xi is the current position. So, the difference of global best minus current position says that how far is the current position of a particle I with respect to the global best of the SWAM. So, that is why this part called as NV. Now, let us understand the velocity components in a graphical way. So, as you can see in the figure, we have xit, which is the current position now, we have vi velocity part, we have local best part, and pgb is the global best part. So, here we are showing the three vectors originating from the xit. Now, the first part is the omega vi. So, you can see this is going to be our first component in the velocity. Now, let us see the other components. Now, since we know the first part is the velocity part or the momentum part here. So, in this momentum part we add our cognitive part. So, this cognitive part, as you can see at the bottom. So, this cognitive part is calculated with respect to its local best. Now, looking at this local best here. So, the direction which is parallel to this local best, we are adding a small component here. So, we will get this. Thereafter, we add a social part which is represented by the green vector. So, when we are adding these three vectors, we are going to get the new position as xit plus 1. So, you can see that these three components basically representing the vector addition of those component with the current position of the particle to get the updated position of the particle. So, we have discussed as till now what is how the position of a particle is updated using the velocity equation. Similarly, so the velocity is also updated using three component called the momentum part or the cognitive part or the social part. While doing this particular process, we have two vectors which we have used. One is called the local best of each particle and the global best of the swarm. So, the question comes that how we can find the local best and the global best. Now, looking at the local best, which is called personal best. So, sometime it is called personal best position or local best position, and in some literature it is also referred as local leaders or personal leaders. So, in this case, so the best position of ith particle in the tth generation is calculated. Here we are assuming the minimization process. So, in problem, so in this minimization problem, the local best of the particle is updated to the new position of the particle if the fitness at the new position of the particle I is smaller than the local best so far found for the particle I. So, since it is a minimization problem, so we are using this smaller than sign. So, if the fitness is like that, we are changing the local best of a particle with the updated position of the particle. Otherwise, we will keep the same local best of the particle. Now comes to the global best. Now, the global best is calculated say in the tth generation. We can calculate as, now you can see that the global best of the particle belongs to one of the local best of the particle. As you can see, say suppose this is the particle 1 and this is the last particle n. So, if we include all of them and we try to find out which one is the local best. So, among those local best particle, one of the particle will be the global best. How we can find? So, this we say that global best of the swarm is one of the local best of the particles such that the fitness of the global best of the swarm is the minimum among all the solutions. So, in this case what it is suggesting is, suppose we have 10 particles, we know their local best. So, we have 10 local best of each particle. If I am going to compare the fitness of these best position of the particles, among them whosoever is the best will become the global best of the swarm. So, this is the way we are calculating. Or in general, at the bottom equation number 4, it is written in terms of vectors. since global best of the swarm is one of the column vector, this we find based on the minimum fitness of the particle, one particle or the local best of the particle. Now, here since we are using our capital L as a number of a particle, so you can see that all the local best of the particles are included to find the global best of the swarm. Now, let us understand PSO algorithm. This PSO algorithm first we will understand through the flow chart. In PSO, so this is the flow chart of the PSO. In this case, we have we start with the random initial population and then we evaluate it. So, these two steps are the same as what we know from the genetic algorithm, or we can say the generalized framework. Then we enter into the decision box based on the number of generation. Now, assume that T is smaller than capital T. So, the first new step which you can see here is we have to update the local best of each particle, as well as we have to find the global best of the swarm. Once we know that, then we are in the another loop with respect to the number of particle. So, the operations that are to be done, we do it particle wise. So, first operation on the particle is we have to update the velocity as given in the previous slide. Then we update the position here. So, this new position will give me the new column vector. Since it is new, we have to evaluate this particle and assign a fitness to it. Thereafter, we increase the counter by 1. This process will be repeated till we have gone through each and every particle. So, in this way, we have calculated the updated velocity as well as the updated position of each particle. Once it is done, we increase the counter of number of generation by 1, and then we keep on moving in this particular loop till the termination condition gets satisfied. Once it is satisfied, we terminate PSO and we report our result. Let us fit our particle swarm optimization into the generalized framework of EC techniques. So, as you can see here, we start with the solution representation. So, since we are using PSO for a continuous search space, so we have to store those values. So, it is called genetics, as we know. In step number 2, we give the required input to start our PSO. Then we initialize our swarm. So, this swarm we generate randomly, and then each particle is evaluated. So, basically calculating the objective function, constraints, and then we assign a fitness. So, till step number 4, all these steps which we have done similar to GA are the same. Thereafter, in step 5, we are in the standard loop of number of generation. Now, step 6 is something new. Why? Because we have to find the local best of the particle as well as we have to find the global best of the particle, and that is why it is referred as a new step. Now, there is a small change in this generalized framework, that we have one extra for loop here. This for loop is basically to update each particle one by one. Therefore, what we do here is, inside, first of all, we have to find the updated velocity in step number 8. Once we calculated the velocity, we have to update the position. Now, the position update means we are changing the column vector of decision variable. So, we can say that this is the variation in the current swarm by updating the position. Now, since the position has been updated, we have to calculate the particle, the new position of the particle, and we can include in PT plus 1, because in the particle SWAM optimization we keep on changing the position of the particle and we do not keep another population such as offspring population with respect to GA. There is no step 12 in as far as the survival, because we do not have any offspring. Every time we update the position of the particle by keeping its local best and finding the velocity with respect to the local best, global best and the previous velocity. So, here these small changes if we can make into our generalized framework, we can fit PSO into this framework of EC techniques. So, let us understand the working principle of a PSO with an example. As you can see that we have taken the Rosenbrook example here, and which is currently we have taken for 2 variable. The bounds on 2 variables are from -5 to +5. On the right hand side, on the third axis, we have taken logarithmic of the function, so that we can see the nature of the surface, and at the bottom, which is x1 and x2 plane, we can find the contours of this particular function. So, since we know this function has many local optimum, but there is one global optimum which is at 1 and 1, and the function value at this solution is 0. Let us begin with the initial SWAM, in which we are considering that there are 8 particles, and since it is the first generation, so we are saying that T is equals to 1. So, let us generate this initial SWAM. Since it is generated randomly, so you can find it out that for all 8 particles, x1 and x2 values are generated for Rosenbrook problem. Similarly, if we look at the third column of this table, the velocity is currently assigned as 0. So, since we can take any value, so we are starting with the velocity 0. Now, thereafter we have to evaluate this SWAM. So, we know that our objective function as given on the top, we have to include the value of x1 and x2 from the previous table to find out what is the function value. So, for solution 1, we have x1 and x2 value. So, we are representing in the column vector of decision variables, putting into the objective function, we get the function value as 357.154. This process we can repeat for each and every particle, so that we can find the function value. So, you can look at the third column that the function value of each particle is calculated and reported here. Now, here since we have to assign a fitness to each particle, as of now we are considering the fitness is the same as the function value. We are at the t equals to 1 generation. So, we are going into the loop. Inside the loop, the first task which we have to do is find the local best of the particle. So, the local best, since it is the first generation, we did not know the previous positions. So, what we do here is that the local best of each particle is itself, because it is a first generation. So, you can look the second number column and the fourth number of the column, all of them are the same. It is only because we are assigning its current position as the local best for each particle in the iteration number 1. Now, once we have calculated the local best of each particle, now we have to find what is the global best of the SWAM. So, as we know the formula given here, what we have to do is we know each particle. So, the fitness for each of the particles. So, I should say these are the fitness of the local best. Among those fitness, what this method say, what this global best says that which particular local best is having the minimum fitness value. So, as we can see that 167 is the minimum value. So, the global best in the generation number t corresponding to the particle number 4. Now, looking at this particular column vector here, the same column vector is copied at the last column. So, this last column is corresponding to the global best of the swarm in iteration or generation number 1. So, once we calculated the local best and the global best, now we have to update the velocity. In this particular velocity, as we know, it includes 3 components as we have understood earlier. Now, let us see how we can calculate this velocity. As of now, we are assuming that omega is 0.75, constant C1 is 1.5 and C2 is 2. So, these are the 3 inputs we have to give to PSO to start with. Now, since in this equation it involves R1 as you can see here and R2, both are the random numbers. So, these random numbers we can generate using our computer. So, set of random numbers are given in the table on the left hand side, where R1 component will be used for the cognitive part and R2 will be used for the social part of the velocity. For each particle, distinct random numbers are given. So, let us use them to update the velocity. Consider the particle number 1 on the right hand side. So, let us write, for our simplicity, we are writing the column vector of the current position, which is x11. So, the velocity is 0 as of now. The global best of the swarm, as you can see, local best of the swarm as of now is the same as the particle, because it is the generation number 1. The global best we have calculated in the previous slide, we have copied here, and the 2 random numbers R1 and R2 we have taken from the table which is on the left hand side. So, let us find the component of velocities variable wise. So, first component, as you can see here we are representing a term and the last component is V11. So, that says that this is the first component of the velocity. So, now we are putting everything into the equation as given on the top. So, we are going with variable wise. Now, this particular part, as you can see, we have underlined. It is only because to see that at iteration or the generation number 1, the personal best has or the cognitive part has no role, because the position of the particle itself is the local best of the particle. And then we have the social part at the last. Putting all together, we get the first component of the velocity of particle 1 is minus 1.779. Similarly, including the velocity, and for the second component we can calculate and we get the second component of the velocity for particle 1 is minus 0.822. Let us perform the calculation one more time for a particle number 2. Here we have mentioned the column vector of the current position of particle 2. Velocity will be the same, will be the 0, because we started with the 0 velocity, and we have the local best of the particle, and similarly we have the global best of the particle. Now, by putting all of them together and taking R1 and R2 from the table in the previous slide, we can calculate the velocity, the first component of the velocity here coming out to be 0.893 for particle 2, and again including into the formula we will get the second component of the velocity for a particle 2 is 2.212. Now, if we perform this same kind of calculation, basically using the formula, putting the value of xi vector, that is the current position, the local best of the particle and the global best and the velocity, we will calculate all the velocities, all the component of the velocity for each particle. So, the table on the right hand side shows you the component of the velocities for each particle. Now, there are two columns which we have put in a red color. It is because you remember that the variable bound for a given problem is lying between -5 to +5, but this particular component are already a large value which is more than +5 in case of velocity for solution for a particle 3, and it is less than -5 in case of particle 8. So, these two components we are showing that when we are performing the row operations to calculate the velocity of the particle, one or both of the component can go beyond the limit of the variables. Since we have calculated the velocity of the particle, now let us calculate the position. So, this is the updated position of the particle. Since the formula is so straightforward that we have to just add these two components. So, let us see these two things. Now, in this table, the column number 2 represents the position of the particle, this represents the velocity, the updated velocity, and here one particular row of solution 4 is made in an orange color. It is because the velocity component is 0. Why it is so? Since it is the generation number 1 in which the local best of the particle is same as the current position. So, the cognitive part will become 0. Moreover, when we calculated the global best of the particle, we know that the particle 4 was the global best. So, meaning that when we will be doing the difference between the global best and the current position of the particle, the social part is also 0 for solution 4. Now, we are left with velocity component. Since we are starting with the 0 velocity for all particle, so it means it says that the updated velocity for particle 4 is 0 because it is the local best, it is the global best, as well as the initial velocity is 0. Now, since it is a simple addition of the vectors, you can see in the table on the right hand side that we have the updated position for each particle. Now, the row number 3 we made it in a red color because the second component of this particle has the value more than 5, and since the limit on the variable is from -5 to +5. So, this particular component, as you can see, which is the second component 5.893, which is more than that, then we have to keep this particular variable on the bound. So, as you can see at the bottom, so limit on x2 is -5 to +5, therefore, we keep x2 of solution 3 on the bound, that is 5. So, since we have calculated the position, updated position, so we have to evaluate it. Now, here the component of the particle 3 is again shown, and just to show you in an orange color this particular component. So, the second component of the particle 3 was out of the bound. So, we kept it at 5, and accordingly the fitness is calculated. Now, the fitness of the position after fitness of the particle after position update, all of the quantities are given in this particular table on the left hand side. Just to see, when we started this initial swarm, the best particle was 4 and it has a fitness of 167.414, and after applying the velocity update and the position update to get a new position of the particle, what we found that the solution 7 is updated, and this is the position, or this is the new position which has the better fitness than the initial swarm, and that is what we expected from every evolutionary computing technique, that generation by generation using the operators the solutions should improve, and all these solutions or particles will move towards the optimum solution. Now, at the end we increase the generation counter by 1. So, currently we are at the generation number 2. So, generally for the algorithm we go for one generation, but since in PSO when we started the velocity was kept 0 as well as the local best of the particle was the same as the current position of the particle. To understand more on this particular phenomena, we will show you the hand calculation for one more generation. So, let us start with that. So, first component is we have to update the velocity. So, the given according to the given formula we are using the same concept. We are keeping the same value of omega C1 and C2. We generated another set of random number R1 and R2 because those are needed in the cognitive part and the social part. Thereafter, we calculate the first component of the velocity for particle 1. As you can see in the right hand side, we have the updated position, we have the updated velocity R1 and R2. To include this particular this particular calculation into the velocity, first we have to find what is the local best of this. How I can find it? We have to compare the fitness. As you can see, the fitness in the previous position and this is the fitness at the current position. So, what we can see that the previous position was better than the current position. So, the local best of the particle is its previous position, that is the PILB2 remains the same as the previous one. Now, we have calculated the local best, but to calculate the social part, as you can see on the top, we have to find the global best of the swarm. So, in this case we have to first find the global best and then we can use the formula. So, this process goes like that. We have to find the local best of each particle first, then find the global best of the swarm and then we can update the velocity. So, let us see how we have updated the local best. Now, looking at the table on the left hand side, particle 1, this we discussed in the previous slide, we compared the fitness and the green color shows that the previous position was better. So, the local best remains the same. For the particle number 2, the green portion shows that the updated position has a better fitness. So, therefore, the local best of the particle is updated here. Similarly, if we compare all of the particles position, the previous position and the current position. So, in this case what we will find that the new position has updated the local best of the particles. Now, since we have calculated the local best of the particle, we have to now update the global best of the particle. How we can find? We will be looking, I am just looking into the green part here. So, if I compare the fitness of the local best of the particles which are in the green color, among them the best is corresponding to solution number 7, meaning that this solution 7 will become the global best of the swarm and PG2 will become the global best of the swarm for generation number 2. Now, using the formula we can update the position since we already know the formula and calculations. So, by putting all of them together, you can see on the right hand side the velocities, the component of the velocity of each particle is updated. Now, this component will be used to update the position of the particle. Since we have calculated the velocity, the updated velocity in the previous slide, now we have to calculate the updated position of the each particle. It is done using the simple formula as given on the top. So, the table on the left hand side, column 1 represents the current position of the particle and the third column represents the updated velocity of each particle. As the formula is so simple, we have to just add those components, two vectors basically, to get the updated position of each particle. Now, here in this table on the right hand side, what you can see that the particle 3 and 6 and 8, they are made in red color. It is because you look into the component here, the basically the this particular component. So, this component is greater than 5. Now, look at this particle 6, this component is also greater than 5, and look at the solution number 8. So, the x1, so the first component of the particle is more than 5. So, what we have to do here is we have to keep them on the bound. So, as you can see at the bottom, variable x2 of particles 3 and 6 and variable x1 of particle 8 are out of the bound. So, we have to put them on the bound, that is 5 as per the question given. Now, in this case the blue column, blue rows corresponding to the particles 3, 6 and 8, they are changed. As you can see, we have written 5 because they were out of the bound. Now, just looking at the third column, so this third column says that when we have updated the particle position and when we find the fitness of them, so the fitness has been improved to 13.22. If we compare the fitness with respect to the previous generation, in the previous generation on the right hand side, you can see that the best fitness we get is 153, but in generation number 2 we get the best fitness as 13.222, and that is the whole motive here, that the velocity update and the position update, which behave like a variation to the for the particle which updates their position, they should be changed in a way that the particle should move towards the optimum solution. In a way, every generation the fitness of the particle should improve, as we can see from the left hand and right hand side tables. Now, come to the graphical example here. So, the same iterations or the generations which we have gone through, we will show how the particles are moving towards the optimum solution. So, this was the initial swarm, as you can see, and the red dot, as you can find it out, is our optimum solutions, and the solutions which are shown in the blue color, they are distributed randomly in a plane of x1 and x2, and the contours of the functions are also shown here. Now, once we have started with the random swarm, we have to find the local and a global best. As we know, this is the iteration or the generation number 1. The local best is the same as the current position of the particle. So, that is why you cannot see any change in the local best. However, to find out the global best, we have to find which particle or which local best of the particle has the least fitness. So, accordingly, this pink color point suggests that this is going to be the global best of the swarm in iteration or generation number 1. Thereafter, we update the velocity. So, here the vectors are drawn to understand how the particles are moving. So, let us see the particle number 1 here, and this was its current position, and when we are adding all the 3 components, the particle is updated to this. So, it is not a particle, it is a velocity. So, the velocity is updated. So, the particle will be updated according to this velocity. So, this particular component will be the addition of the vector component. Similarly, looking at the solution number 2, this is the current position of the particle. This particular arrow which is drawn in a pink color is the velocity component added to it, and finally, we get the new position. So, every particle from 1 to 8, the arrows are shown, those arrows represent the velocity component of each particle. Thereafter, we have to update it. So, the current position plus the velocity will give us the updated position of each particle. So, those are shown in those black circles, and you can see that the solutions have started moving towards the optima. We have done one more generation to understand the local best and a global best. So, in this second number of a generation, so velocities are updated. So, in this case the solutions are shown and the velocity components are also shown, as you can see for every particle. Once we know the current position and the velocity update, we will get the updated position of each particle in the generation number 2. So, these pink dots all are the updated positions here, and we can see in the generation number 2 solutions are again started moving towards the optima, which you can see in the red dot. Let us compare how the solutions have moved so far. So, this was the initial swarm where the solutions were randomly generated in x1 and x2 plane. After 2 number of generations, you can see how these pink points are moving towards the optimum solution, and this process, when we will be continuing for further generations, we will find that these solutions or the particles will move to the optimum solution, or the particles will locate the optimal solution for the Rosenbrock problem. So, with this particular introduction and the working principle of PSO, let us come to the closure of this session. So, in this session, what we have gone through is the introduction of the particle swarm optimization, since it works differently than the genetic algorithm. So, we have gone through the PSO, its development based on the flocking of the birds, and thereafter once we understand the physical or the biological phenomena or the process of the swarm, there are 3 distinct features that we understood. So, those 3 distinct features we understood as a global best, local best, and the velocity and a position update of each particle. Once we did it, we have certain formulas to update the velocity of the particle. It constitutes of momentum part, cognitive part, and the social part. And we have also gone through the graphical illustration. So, what we understood that the velocity of each particle is the summation of 3 vectors, whereas the social and the cognitive parts are the vector operation, that is the difference between the 2 vectors. Thereafter, we have gone through the position update. So, it was a simple formula to use it, and we understand the PSO with the help of a flow chart. So, in that flow chart, a new addition was done in which the position update and the velocity update was done for each particle one by one. We also fitted this PSO on the generalized framework, so that we can see what are the small changes we have to do it, and the same generalized framework we can use it for particle swarm optimization. We understood this particle swarm optimization through the through the example of a Rosenbrock function. So, we understood each and every component such as local best, global best, velocity update, and a position update, and we perform two hand calculations for 2 generations. And the same example we have shown graphically to understand how these particles have been they started with a random position in the initial swarm, and after performing 2 generation, the fitness has improved a lot, and if we keep on continuing, the particles will finally move to the optimum solution. So, with this I conclude this session on introduction on particle swarm optimization. Thank you very much.